Hey ChemStars, this is Mrs. Vandalay bringing you another ChemStar video, and we are in section 5.3, which is electron configuration and periodic properties. And this entire section, it is all about attraction. And being typical teenagers, I'm sure you understand the idea of attraction, all right? But something else we want to bring about in this section, it is a periodic properties. It is a cyclic property. It repeats itself, okay? So these properties are like a repetition. You remember in the video that we watched about the history of the periodic table, and the guy was like smelling all those different elements. And he said, ooh, chlorine stank. And then he smelled all these other ones that had no odor. And then the next thing you know, bromine right underneath chlorine in the periodic table, it stank. All right, that would be, in a sense, a periodic property. Okay, odor in a sense. Okay, but we're not going to be testing odor, thank goodness. All right, but we're going to be looking at other things that will help explain things that are going to happen down the road in chemistry. Okay, so what is this periodic law? What is this periodicity? It says that a physical and chemical properties, such as odor, if you will, such as reactivity of the elements, are periodic functions of their atomic numbers. And folks, what's an atomic number again? It's the number of protons. And boy, is that an important idea right here. Okay, this idea of the number of protons. So this is kind of like that activity that says with the element cards, you may or may have not done the element cards, you may have done the missing cousin activity instead. So we were looking for repetitive patterns in either activity, okay? And that's what we're looking for, again, are these repetitive patterns, okay? Now I set up here, it's all about attraction. So I want to spend this first part of this lesson talking about attraction, okay? And what are we talking about? Attraction between what and what? Well, let me tell you. So this whole thing can be discussed about the attraction between the protons in the nucleus and the outer electrons. Every single thing we talk about in this section, 5.3, can be thought of in terms of the attraction between the protons, the positive charges of the nucleus, and the negative electrons in the outer rings. Okay, so what's going to happen as you go across a period? All right, what happens? The attraction increases. Why? There's more protons. So if I want to take a look at, let's say, here's one, and I'm going to call this lithium. How do I know it's lithium? Well, it has 1, 2, 3 protons. All right, what's the atomic number? It has 3, it's lithium. And then I'm going to compare it with oxygen. How do I know this oxygen? It has 8 protons, okay? So here's my outer electron. And where is the attraction going to be greater? Will the electron with 3 protons or the electron with 8 protons? Well, with 8 protons. Why? If there are more protons, there's greater attraction to the outer electrons. There's more things pulling on it, okay? So what about as you go down a group? All right, let me move oxygen out of the way here. Or if you want to draw that, that's fine. But what happens? Well, if I go down the group, what's going to happen? I don't know if you can tell this, but I have more shells. All right. So there's actually less attraction. Why? There's more shells. So what does that mean? If there are more shells, then this electron out here is further away from its nucleus than in the first shell. So maybe this is 1 shell, and this may be 3 shells. That third shell is a lot further away than that first shell. So if they are further away from each other, there's going to be less pull. Think of magnets. Here, my 2 magnets are really close to each other. They're going to go smack, and they're going to be attracted to one another. And they're going to, don't put your finger in between, all right? Ow. Okay, but what if I pull my magnets apart? What kind of pull is there going to be? Much less. Okay, so let's scroll down and let's check this out. And here's our periodic table, and this is how I see it. Now, you know, I was a teenager once, and that was back, well, I won't tell you how far back, let's say in the 80s, I was a teenager. And Indiana Jones came out, and I thought Harrison Ford was just the most, wonderful man out there. So I was highly attracted to Harrison Ford. So if I look at this, here's my Harrison Ford. He's going to be my proton, and I'm going to be the electron. Okay, so over on the left-hand side, they have fewer relative number of protons than over on the right-hand side. So I have more Harrison Fords over on here. So let's just think about it. Where am I going to be more attracted, on the left-hand side if I'm the electron, or on the right-hand side? Definitely on the right-hand side. Okay, and as I step further and further and further away from Harrison Ford, what's going to happen to my attraction? It's going to get less and less and less until maybe I can't even see them anymore. Okay, so that's what's going to rule this entire discussion. Okay, so let's just start off. Which one has greater attraction? And yours is like blurred out, so you really can't see it. I found that too, so I just made up two. So why don't you make note number one is either magnesium or chlorine. So here's my magnesium, and look over here. Here's my chlorine. So they have a relationship. They are in the same period. All right, so let's look up here. As you go across the period, the attraction increases. So which one's going to have greater attraction? Magnesium, chlorine. Which one has more protons? Well, this has 12 protons. Chlorine has 17 protons. So chlorine has greater attraction. Why? It has more protons. Well, what about magnesium, right here again, or barium? They're in the same family. They're in the same column. Which one has greater attraction? Well, what did I say up here? As you go down the group, the attraction decreases. Why? There's more shells. Those outer electrons are a whole lot further away with more shells than over here. All right. And I can also like think of this as, hang on, as the further away I am, again, the less attraction. I can't see them. So I can't be close to those protons. I can't be close to Harrison Ford. All right, so which one has more attraction? The one that's closer. I can almost reach out and touch Harrison Ford the closer I am. So that would be magnesium. Magnesium only has 3 shells. Barium has 6 shells. All right, so magnesium is closer. So I'm going to write why it has fewer shells. Now what? Let's look at here's strontium over here, and phosphorus is over here. So it's a diagonal. All right, well, it's a win-win situation. All right, so phosphorus does. Why? It has relatively more protons. It's on the right-hand side of the periodic table and fewer shells. There's truly a very fancy word, this idea of relatively more protons. So if you're just looking at over here, it's actually called effective nuclear charge. All right, if you want to go ahead and take AP chemistry, we're going to talk a whole lot more about effective nuclear charge. But if you just trust me in the idea that I understand that barium has, 56 protons and phosphorus has, I believe, 15 protons, I understand barium has more, but it's in the relative position on the periodic table. So when I say relatively more protons, I mean it's over on the right-hand side, okay? If you want a better explanation, sign up for AP, okay? Just trust me on this. So relatively more protons and phosphorus, fewer shells. So it's a win-win situation. So if you're looking at a diagonal going this direction, always pick the one in the upper corner. That's going to always have more attraction, okay? So let's take a look at our very first actual property. I hate to say this, but attraction is not a true physical property, but it explains all these other periodic properties that we're going to talk about. So let's go ahead and turn the page and let's see how this works with atomic radius. Okay, so this next section is about the specific periodic properties. So it says, I can explain and predict the trends based on the position of the element found in the periodic table. I can compare the atomic radii, ionic radii, first ionization energies, electronegativities based on the position of the element on the periodic table. Okay, and there's your vocabulary. So if you're in level 1 listening to this, you are going to go ahead and learn about ionic radii. If you're in level 2, we're going to skip ionic radii. Okay. So what is the what is the atomic radii? It is, if you have, let's say, an elemental form of, any element, lithium, okay? I just saw lithium there. It is the distance, it's really take the distance between the 2 nuclei of 2 adjacent lithium atoms, and you take, half the distance. That would be the atomic radii. So look what's happening here. there's numbers and there's also a physical representation. So as you go across the period, what's going on? 152, 112, 85, 77, 75, 73, 72, 71. What's going on as you go this direction? All right, atomic radii is doing what? It is, I'll put it over here, decreasing. All right, why? Well, think about it. What did we just talk about? We just talked about attraction. All right, so folks, I know you understand attraction. I see it out in the hallways. If you are attracted to that certain someone, I can tell by your physical proximity to that certain, even in the age of COVID, I can tell by that physical proximity, if you're attracted to that person or not, you're going to stand closer to them. Okay, if you don't know that person, if you are unattracted, you're going to be far away. Okay, so what happens if the attraction goes up? Those electrons are going to be drawing closer to those protons. So I wrote, it's all about attraction. There are more protons. The electrons are attracted to the nucleus with more protons, drawing them closer. Okay, but as I go down the group, what's going on here? Well, look at the numbers, 152, 186, 227, 248, 265. What's happening to those numbers? They're getting bigger, aren't they? So that's kind of what this is. Do you recognize these are my Russian nesting dolls? All right, I have a couple pair of these actually. So this would be like my first shell. This would be my next shell, and this goes inside of this one, all right? And these can fit inside of this one, and these can fit inside of this one, and these can fit inside of this one. My last doll is a whole lot bigger than my first doll. So all these dolls are nested inside, just like here. Each of these energy shells are, in a sense, nested inside of here. And they're nested inside of here, and they're nested inside of here. So what's happening? The more shells, the larger. So why? It increases. Why? It's all about the number of shells. All right, the more shells, more layers, the greater the radius. All right. By the way, the attraction goes down the further away it is. All right, and we'll talk about attraction in the next one. Okay, so let's keep going. All right, let's look at this chart next. This chart is another depiction of the same thing that this is doing. All right, this picture right here. But they kind of showed you by atomic number. This is atomic number, so the number of protons, and you can see the radius. So it says, what element has an atomic radii closest to 200? Well, here's 200. Well, it kind of looks like sodium is definitely one. Okay, but what else? What's this one? What's the one just beyond potassium? Hey, what has atomic number 20? It's not argon. I hate to say that, it's 18. It's actually calcium. So I'd say those two are pretty close to 200 picometers. I think calcium may be a tad closer than sodium is. But in general, as you go across the period, all right, so I'm going to use red. As they go across the period, this is going across. This is going across. Do you see what's happening here? This is going across. In general, what's happening as you go across the period? All right, the atomic radii does what? Well, look, it's getting smaller, right? Isn't that what we said earlier? Why? Because you have more protons, you have more attraction. Electrons are getting closer to that nucleus because you have more protons drawing them in. All right, so what about as you go down the group? All right, I'm going to use green for this one. All right, so here's lithium and sodium and potassium and rubidium and cesium. So what's this trend with this green line here? All right, as you go down the group, that's my green line, isn't it? It's getting obviously bigger. All right, why? More shells further away. The atomic radii is going to get bigger, isn't it? So what will barium do? Will barium be bigger or smaller than cesium? Okay, so, where is barium? I don't see it on the chart. Let's look. Oh, here's barium. Barium's right here. Here's cesium right here. Well, the numbers kind of tell you what it is. Barium's going to be smaller, all right, than cesium. Okay, why is that? Well, let me guess. Let's look at it again. Barium has one more proton than cesium does. So what will that one more proton do? Draw in those outer electrons, won't they? Yes, they will. So barium is going to be a little bit smaller than cesium. So what about cesium and francium? Well, where's francium? Francium, if I look at this periodic table, sort of, it's underneath cesium. It's right here. They didn't give you a number, but you can still figure it out. What's going to happen? Francium's going to be bigger than cesium. All right, why? It has a greater shell, has more shells. It has 7 shells. Barium only has 6 shells, all right? Or cesium only has 6 shells. So it's going to be bigger. Okay, let's keep going. All right, so summary of atomic radii. So the question is, which one is bigger? Well, if you're paying attention, the last page we're talking about the greater attraction, the smaller it is. So which one's going to be bigger? The one with greater attraction? No, the one with less attraction. So if I'm going, this direction, if I'm in the same period, I want the one with fewer protons. Therefore, it's less attraction. Therefore, the electrons are more spread out, okay? So if I go, the one on the left is going to be bigger than the one on the right. Well, what else? The one with more shells is going to be bigger. So let's put this all together. Look at my periodic table. All right, I'm going to go like this, then I'm going to go like this. And what ends up happening? Notice where I put my star? That's francium. Right now, when I'm making this video, francium is the largest element there is. However, one day, if you're going to, dig up my video and it's like 20 years old, I bet there's going to be element 119 out there. All right, maybe they're going to call it after me. I have no clue. All right, but element 119 will then even be bigger than francium. But for right now, all right, we have francium is my biggest element. So really, when you're asking which one is bigger, the one that's closest to francium on the periodic table, the one that's further to the left and the one that has more shells is going to be bigger. So I could ask you this, which one's my smallest element? Let's think about that for a second. So which element is opposite of francium on the periodic table? Well, the one that's the further upmost right, all right, and that would be helium. So I'm going to be crazy. I'm going to make this even bigger. Woof, there's my francium, biggest element. Here's helium, my littlest one, okay? Biggest, littlest. So they're asking you which is bigger, lithium, which is covered by, here's lithium, or boron. They're in the same period. So which one's bigger? Well, hopefully you got lithium. Why? Why? It's all about attraction, isn't it? Fewer protons. Lithium only has 3 protons. Boron has 5 protons. There's less attraction to those 3 protons than the 5, all right? Well, what about magnesium, which is right here, and barium? You pick which one's bigger. Think about it for a second. You fill it out. I sure hope you said barium is why there's, more shells. Okay, what about phosphorus or strontium? All right, let's check this out. Here's phosphorus, see that? And here's strontium. So again, we're in this diagonal. So which one is bigger? It's a no-brainer, all right? So strontium is why there are fewer relative protons. And again, you want to say maybe there's a lower effective nuclear charge. That's the official wording for relative protons, all right? And you have more shells, all right? It's closer to francium, okay? That's what you need. So what I'd like you to do is take a few minutes. You may want to pause this and actually try this on your own, all right? Don't be afraid to make mistakes, all right? You can always fix it later, and I'll never know that you made mistakes, all right? But I really want you to think about what I said and fill this out on your own. And, when you're done, unpause this, and we'll go over it, all right? So pause this, do it. I hope you paused it. All right, welcome back. I hope you tried this. So here's the first one. Lithium, potassium are in the same period. That's why there's an arrow here. All right, I'm sorry, I said same period. They're in the same shell or the same group. There we go, same group, same family, same column. There you go. So you're gonna look for the one with more shells, and more shells means it is bigger. All right, what about calcium and nickel? Let's kind of look up here. Here's calcium and here's nickel. They're in the same period, aren't they? All right, so which one's going to be bigger? The one with fewer protons, less attraction, going to be bigger. What about gallium and boron? Here's boron, here's gallium. So gallium has more shells. All right, it's bigger. What about oxygen and carbon? They're in the same period. So look at here, same period. Carbon is going to be bigger. Why? Has fewer protons, less attraction, therefore it's bigger. Chlorine and bromine. Here's chlorine, here's bromine. They're in the same group, so the one with more shells is going to be bigger. That's going to be your bromine. All right. What about beryllium or barium? Here's beryllium, here's barium. Again, they're in the same group, so the one with more shells, all right, is going to be bigger. Silicon or sulfur, let's check those out, okay? Here is silicon right here, and here is sulfur. So again, they're in the same period, so the one with fewer protons is going to be bigger, okay? Then we have gold and iron. So iron is here, gold is here. This is kind of rough, all right? Which one is actually closer to francium? It's kind of hard to say. As it turns out, it's going to be gold. Why? Because gold does have more shells, so it's bigger. And in general, I will not give you one that goes kitty corner in that direction. Like, well, iron is closer to the left than gold, but gold is further down. I don't know. So I'm going to try to stay away from that kind of a relationship. All right. So hopefully this makes sense. And we're going to talk about this in class. So we'll see you next time. I hope this is helpful. Talk to you later. Don't wait to be great. Bye-bye. How was that, Beck?